Good morning. Welcome to the Subsidence and Deformation live stream. So this is the first of 4 sessions. We have 3 of them today and then a final session tomorrow morning. We also have a poster session this afternoon, so please come along, take the opportunity to chat to our poster session participants and have a look at some of the great work that they've done. This morning, the first session, we have 5 great presentations lined up. I'd just like to remind everybody that you can ask questions during the event in the Slido panel on the right, and they will be passed to the participants. And then at the end of this first session, we will have a short question and answer. We'll see if we have time to ask maybe one question or so to the presenters as we go. And if not, then we can address them in the question and answer at the end. So with very little fuss, I would like to introduce the first presenter, who is Guido Luzzi, and we'll be speaking on low-cost artificial reflectors for deformation mapping. Guido, I think you're on mute still. Are you able to activate your audio?
Okay, thank you very much. Good morning, everyone. This presentation describes the development and the test of a low-cost active reflector for deformation monitoring based on the use of Sentinel-1 images. The authors are all from the Centre Tecnologic de Telecommunication de Catalunya. And I heard something, but anyway, I go on. The authors are Pedro Agustin Lopez. Sorry, I heard repeated. Sorry, I have some problem with the audio.
Is there a problem, Guido?
I have some problem.
Do you have Brella open as well?
Sorry. I have some problem. Audio.
We can hear you well. There's just a bit of echo.
Yes, but this is, well, I go on?
Yes.
Okay, fine. But there is an echo from my side. I try to.
Do you have the Brella window open as well? If you do, you need to close that so that you don't get 2 sets of audio.
Okay. I didn't succeed in presenting from this situation. Sorry. I don't know why it happens. Sorry? And when I speak, I have this echo. They didn't succeed in speaking.
We can see your slides.
Yeah, Guido, can I suggest that we perhaps moved on to the next presenter and then come back to you afterwards?
Yes, maybe
okay?
maybe better.
So can I ask Riccardo Lanari, are you able
better.
to take over?
Thanks. Okay, but the audio is a problem.
Do you also have audio problems, Riccardo?
No, if you let me share the screen, then I can start.
Perfect, thank you.
Okay, can you see my screen?
Yes.
Yes. Yes,
Okay,
we can.
so then let's start. I said I'm Riccardo Lanari, and as you can see from the title, my talk is going to be focused on showing some results of a processing experiment we did through the SBUS approach for continental scale generation of Sentinel-1 deformation time series within the cloud, one of the cloud computing infrastructure of the DIAS environment. I kindly ask you to all the other colleagues to mute their microphone, please. Okay, so before I start and go into the details of the presentation, let me say just one word on SBUS, which is the advanced insert technique we use. Probably many of you already know it's based on exploiting a time series of complex images that are coupled in order to generate a redundant set of small baseline differential interferograms, which are combined. Essentially, we solve a linear system of equations through the singular value decomposition, and we get this nice time series like the one relevant to the Campi-Flegrei caldera. That I show to you because this is an evidence of how simple it is for SBUS to integrate ERS and MVSAT data if they are collected with the same illumination geometry. But of course, my talk is not on ERS and MVSAT, although they were beautiful sensors. It's on Sentinel-1. After 3 days of FRINGE workshop, I'm not going into details of this nice constellation, just 3 highlights. The short temporal baseline, in many areas we have 6 days, the nice 250 kilometers watt thanks to TOPS mode and the global coverage. But one thing I even would like to underline much more is what's happened with perpendicular baselines. If you compare what we had with MVSAT and also with ERS and with Sentinel-1, it is clear that there is a reduction of the perpendicular baseline to a couple of hundred meters. And so that's the reason why, because of the short temporal and short perpendicular baseline, we say that Sentinel-1 is a small baseline constellation that clearly very naturally fits with the SBUS technique. That's the reason why it didn't take too much for us to adapt the processing chain we had developed for ERS, MVSAT, Radar, Stratocosmos, SkyMed to Sentinel-1 processing. You have the details, particularly in this paper of Manunta in 2019. Essentially, we had to make some adaptation or implementation. First of all, for what concerns the computational efficiency, because of huge data volumes, I will say a few words more. We had to consider a parallelization strategy based on multi-node and multi-core architecture. Moreover, we have started to extensively exploit the cloud computing environment to have, when needed, the necessary resources to process this huge amount of data. And the second issue is relevant to the algorithm point of view. Basically, the main chain in addition to the burst interference generation was relevant to the use of GNSS data in order to refine our deformation products. But although, let's say, this step is not changed, I am going to discuss a little bit, also looking to other presentation, about the step we call originally multi-temporal interferogram noise filtering, because essentially we have realized that it will be much better to talk about multi-temporal interferograms consistency retrieval. Why I say that? It was already said in this conference, so let's repeat quickly. We are using multi-look interferograms. Okay, if we would use single-look interferogram, we would have any problem of consistency. But if you look multi-look interferograms, and you look at a triple of at 3 interferogram for each pixel, then what you may have is that there is no full consistency. In other words, there is no closure of your face. It's frapped different, doesn't come to 0. And you can intuitively see also by looking at these 3 interferograms. We have realized this consistency problem of multi-look interferogram since quite a bit. And so the first solution we implemented also to improve our phase unwrapping performance starting from 2006 was to group, to generate our small baseline interferogram essentially by using a triangulation for the identification of the interferogram within the perpendicular baseline, temporal baseline plane. Why we do this? Because if you have this triangular structure, essentially for each of these triangles, for each pixel, you have an indicator of your consistency, what we call the temporal coherence, or if you prefer, this triangular coherence, that says to you which are the pixels where you have this good consistency and where not. Because consistency is clearly very important if you use multi-look interferogram assay. But after this step, we did something else. Essentially, we implemented an additional step. The idea in this case was the following. Well, since we have a redundant number of interferograms, let's increase this redundancy. Let's further extend this redundancy, because what is possible to do thanks to this redundancy is essentially to improve the consistency of our data. Essentially, we implement a nonlinear minimization problem based on this redundancy, through which somehow we have regenerated our interferograms, improving the consistency of our phase closure. And the result you clearly see, essentially, we move from this scenario with this other scenario, which much improved the consistency of our data. And you can find details of this in this paper we published in 2015. Now, frankly speaking, what I have to say to you is that in 2015, actually in 2014, when we developed this method, the big enemy of the phase consistency in the multi-temporal interference was noise, because of the large baseline, so there was the correlation noise. Nowadays, there are probably, looking at Sentinel-1 short baseline, additional elements that are fighting against this consistency, but the approach essentially works in any case because it's tailored on closing this loop. And that's the reason why, let's say, I found interesting the discussion in this work on Ansari, Dezan, and Parizzi about the systematic bias that they see in this bus implementation. But by definition, what I have to say is that there can be, for sure, implementation where there are these bias. But by definition, because of this phase consistency step we have, essentially, there are no bias if you're applying this processing strategy of the piece bus approach, of the parallel bus approach. But to fully convince you, I bring these few experimental results to you. Essentially, we are using the same data set relevant to this beautiful area in Sicily of Ansari and colleagues. Actually, we slightly shifted a little bit the Fourier windows to 2016 because there are in the IPF focusing inconsistencies for what concerns the image at the end of 2015. This is the overall interferogram networks we generate, through which we apply this consistency step we developed quite a bit ago. And now, once you have applied this consistency retrieval step, any triangulation you use or any configuration of interferogram you use, the consistency is guaranteed. So if you look at your mean deformation velocity, they are always the same. They are fully consistent. But to fully convince you that there is no bias at all in our implementation, here you see the differences of the mean velocity. Short time interferograms minus medium time interferogram, short minus long time, medium minus long time, you see it's everything green. And if you look at your time series, it's 0. 99% of this is 0. So there is no bias at all, except for a few areas like the P21, where you see this red spot. But this is not a bias. This is a phase unwrapping error, which is due to the high fringe rate because of the volcanotectonic crisis in 2018. So the lesson is that there is something occurring, but these are the phase unwrapping errors, and they occur in the long-term interferogram, not in the short-term interferogram. But the most important thing to say is that when you use short time interference with respect to long time interference, you have a huge increase of your temporally coherent pixels. And so I was a little bit astonished to hear also in this case that with such a nice small baseline Sentinel-1 constellation, it's dangerous to use small baseline interference. I disagree. Small baseline interference, if they are properly process brings to you less phase unwrapping problems and huge increase of your pixel density. So they bring to you huge information, and then of course they must be preserved. But all this discussion you can find together with the link to the data in this comment that we have just submitted, and that probably is already available because we made open. So once it's clear that in our PISBUS implementation there are no bias at all, let's say if we can improve, if we can refine our products by using GNSS data, there are a lot. In particular, there are those fully open provided by the Nevada Geodetic Laboratory. In this case, unfortunately, some of these freely available time series have some gaps or some jumps because of the antenna changes. So it's needed, first of all, to make a screening and a selection, essentially, in order to remove the outliers, so to move from much more effective results, a little bit less dense, but much effective. And thanks to this, we have implemented a very simple step in order to get refined products. It's sketched here. Essentially what we do, it's simple. As I say, we have our raw products coming from PISBUS. These are the interpolated GNSS information projected in the line of sight. Please look at the difference of the scales. This is only for visualization purposes. And then what we do, essentially, we remove the low frequency component coming from the GNSS data. And then we have a more stationary signal where atmospheric filtering can be better implemented. And then finally, we add back this GNSS information, this low frequency component information. Then, of course, we have two products, you see, one without this low pass component, one with. We typically show this one because of the better consistency in the overlapping areas of the different patches, but it's essentially, we have both products. And now the last point is relevant to the data volume. If you want to make huge processing, the data volume are big. I took this old slide, which is still valid. You see, starting from 2018, we have to face more than 12 terabytes per day in terms of data volumes. So processing huge amounts of Sentinel-1 data means to make a lot of processing. And so the idea for our experiment was to say, okay, instead of moving all these huge volumes to our computing facility, let's do something opposite. Let's benefit of the DIAS infrastructure and install on one of these cloud computing infrastructure DIAS the entire pipeline. In particular, we selected the Honda one through a public tender, where essentially our PISBUS pipeline was installed. The data, the Sentinel-1 data were already there. We essentially simply ingested the GNSS data coming from the Nevada Geodetic Laboratory and made the entire processing here. And you find also a little bit of details about the computing infrastructure we use. In our experiment, which has been developed within the EPOS infrastructure, essentially we have processed 175 tails of 200 by 250 kilometers. Most of these 150 covering the span between March 2015, September 2018. For a bit 20 of these relevant to Italy, because Italy is beautiful, we extended the investigated time series. Okay, it's a joke. It's not only because it's beautiful, but because we have a contract on this. So this is the entire data set that we have used in our experiment, and what you see here, it was successfully processed. You see the mean velocity map, but you also see different sample time series that could successfully retrieve it. You have this jump in the time series of the Lefkada earthquake. This is the uplift of Campi Flegrei caldera. We retrieve oscillations, non-linearities due to mining in Germany and Poland, landslide and whatever, because our processing strategy is not based on any modeling. And this is the last view graph to show you a summary of what we did. Through the implementation of the piece-based approach in 6 months and with 60,000 euros cost of computation, we could process the entire 72,000 image of the considered 175 frames, with our multi-looking giving to us 80 by 80 meters, and we successfully retrieved more than 120 million pixels. We hope that this technology could be used for the European ground motion production. Unfortunately, this was not the case, but we hope that at least it can be used for the validation of this important Copernicus service. And that's it. Thank you very much for your attention.
Thank you, Riccardo. Very interesting. I'll remind everybody that we'll have all the questions in the question and answer session at the end of the session, and you can put all your questions into the Slido chat on the right-hand side of your screen. Please address which speaker you have the question to, or note which speaker in the question. We're now going to go back to the first presentation of this session. Guido Luzzi has fixed his audio problems, and he's going to talk about the performance of a low-cost active reflector for deformation monitoring using Sentinel-1 images. Go ahead, Guido.
Okay. I need to be shared. Can you give me the sharing of the... I need the share. Okay, fine. Okay, thank you. Sorry, apology for the problem. Okay, so after the
just the opposite choice, duplicate.
It's working now. Can you see?
No, you have to change the configuration again. And that menu on the top. Yes, perfect.
Okay, fine. So, can you hear me? Can I go on? Please, can you hear me?
Yes,
yes.
Okay, fine, thanks. Okay, well, passive corner reflectors are very common when you need targets for amplitude and phase check, because they are very stable in phase and amplitude. They have usually a low cost and also a simple design and implementation. But sometimes, especially in areas where coherence is very low, and like as for example mountain slopes, snow-covered area, glaciers, the severe weather condition can compromise their performance, and also they are burdened, so the installation is very hard and also very costly. An alternative to the passive corner reflector is represented by active reflector. An active reflector is basically a simple device which receives the signal from the satellites passing over it, and after an amplification, send again the signal with the higher strength directly to the receiver of the satellite. Usually, the advantage of these devices is that they are very easy to be installed, compact, and flexible. But with respect to passive corner reflector, there are two drawbacks. One is that you need a power and energy source, so there is a power consuming, and sometimes very often they are sensitive to temperature. This is due to the fact that the electronics can be affected by the variation of temperature, especially when you are using for a long temporal interval. So there are different concepts of active reflector. There are the top-level transponders, which are, for example, CALIBRATED from DLR or other system from China, where you have the top performance because you need the highest accuracy in amplitude and phase measurements. But the cost is very high. The installation, they are not apt for the installation on field. Since 10 years ago, some active reflector to be used in field campaign were proposed by some companies, but to my knowledge, today only the electronic corner reflector from Metasync is available. It is an apparatus available for field campaigns. It's capable of to measure vertical displacement nominally 1 millimeter. It is a bit smart because it has very good user-friendly control software and the moderate cost. In this configuration, the situation is a bit different from what we are proposing. We propose an active reflector which can provide a phase performance cost benefit and especially low power consumption. This to make feasible the setup of very dense network. Our goal is an accuracy of about plus or minus 2 millimeters, but it is based on the simple and low cost design. The goal of this kind of devices is to make possible the distribution over large areas and in areas where it is difficult to install power, the power of the device. Okay, the basic, the starting requirements for an active reflector, as for a passive reflector, is the radar cross section to guarantee an adequate accuracy in amplitude and phase. The radar cross section must be, in general, higher than 40 dB per meter. In this case, I'm talking about the Sentinel-1 case. This, just to give you an idea, is the radar cross section of a triangle whose size is 1.7 meter. We take this value as a reference for our design. There are two main factors which influence the design of an active reflector or this active reflector. The first is the gain of the antenna. We stress the performance of the antenna because it is very important to have the higher gain to allow a lower gain of the radio frequency section. This means that if we have the top of the gain from the antenna, we can reduce the gain of the radio frequency section. This means that we have a lower consumption and simplest design of the device. In this slide, you can see a picture of of one of the prototypes, and the first step we were carried out due to the fact that the main factor affecting the performance of this device is the temperature, was to test the radio frequency section through a measurement setup which use a kinematic chamber. We change the temperature and we simulated the signal from Sentinel-1 to using a vector network analyzer. So we can estimate, by this single setup, the effect of the temperature on the global response of the device, and also how the transfer function of the device can affect the pulse of the satellite, the synthetic pulse. Of course, these first tests were satisfactory. The second test we carried out was a test of the complete device. We use a close range setup. Here we use the same typical signal to produce a measurement. We was carried out for different days. In this case, you can see a plot of 3 days of measurements. And this is the case of the amplitude. We are looking for the stability of the amplitude. You can see that there is an instability which is strongly related with the temperature, which is the blue line. But the instability in thermal amplitude is satisfactory from our point of view, about 40%. But the most important information is the information concerning the phase stability. And here you can see that with the temperature varying of about 20 degrees Celsius, we have a behavior of the phase response which is not satisfactory. By the way, we were able to detect a fit curve which will be used, as you will show later, for correcting the data in a real case. Okay, the last and the most important test was carried out in a real situation where we, in the campus close to our institute, we installed an active corner reflector, and the passive corner reflector smaller than the one cited before. which was used for reference. Well, we first check the functioning of the apparatus, for example, using the app available from the browser of the Earth observation. You can see that the signature of the active reflector is very clear. We take also some measurements of other points of reference and of the passive cone reflector. You can check every 6 days. You can check. We and you also, the listener, can check the functioning of the devices through this tool. But the results of almost 1 year of measurements was not fully satisfactory. But because if you can see that the red square, which are the raw data, the raw phase data, are very sensitive to the change of temperature over the year. But after the correction, the situation improved a lot. We also take profit of this measurement to measure two parameters of main concerns in understanding the behavior of the active reflector. The first is its actual radial cross section. We make this measurement making a comparison between the signal acquired and calculated theoretically for the triangular passive cone reflector and the AR. And then we also calculated the signal to clutter ratio, which was calculated according to a typical method proposed also by other authors. This value and these two values are compliant with the accuracy of the phase measurement, because they influence on the accuracy of the phase measurements, which is within our goal. We also make another campaign in Slovenia, and the behavior of the data is very similar. You can see the not correct data have a strong influence of the temperature, but after the correction, the data improve a lot. Just to summarize the results of these two campaigns, you can see that from this table that if we also, both in Slovenia and in the campus in Catalonia, after correction of the data, there is a very good standard deviation concerning our goals, which is lower than 2 millimeters, was the goal, and better in the case of the campus. We have also to underline that all this data collection, which is ongoing, was very interesting because it confirmed that the temperature is the main challenging issue. The stability with the temperature is the main challenging issue of the project. And we also have a good and satisfactory result that the setup, also the two different setups in Slovenia and in Catalonia were a bit different. The correction, the fitting curve used to correct the data was functioning in both cases. There is a drawback in the present configuration, and it is that the actual correction is carried out offline. I mean, we collect the data and then we use this data and the fitting curve to give the final corrected data of phase. But it is planned for the next steps of this study to include the sensor now include a temperature sensor. So we have data for making the correction, but we are evaluating the possibility to build in a hardware and software tool for a real-time correction. This goal must take into account that, of course, these new tools could worsen a bit the power consumption and also the stability of the system. Well, just before to thank you for your attention, I've spoken till now of high, moderate, and low cost. These are only relative terms. I can see to give you a rough estimate of these quantities that our prototype now in the actual version is below 1,000 euros, but the idea is to provide an integrated system which can be with the cost very close to the cost of one passive corner reflector. Thank you for your attention.
Many thanks, Guido. So we're running just a couple of minutes late, so I would say let's leave all the questions until the question and answer session at the end. And I will like to introduce Michele Crosetto, our next speaker, who is going to speak on the Copernicus European Ground Motion Service. So all yours, Michele. We can see your screen share in the WebEx. Michele, you're still on
Michele, you
mute.
need to unmute, yes.
Yes, can you see the presentation?
Yes, we can.
Okay, so good morning, everybody. I am going to describe the Copernicus European Ground Motion Service. This is an important and ambitious project of the Copernicus program. The authors of this presentation are all coming from the advisory board of this service, with the exception of Lorenzo Solari, which is the interferometric SAR supporting expert of the same service. Let's see a bit the context of this. The context of this project. In the last year, there was an increasing discussion within the interferometric community and an interest to launch a European scale deformation service. In 2016 was established a European Ground Motion Service Task Force, which was led by Michaela Frey from the German Geological Survey. This task force worked through 2 years and ended its work with a white paper, which was published in 2017. In this paper, there were 75 participants from more than 20 countries. Here you have the link to this document. At the end of the same year, so in 2017, there was a very important step. The Copernicus User Forum and the Copernicus Committee added the European Ground Motion Service to the Copernicus Land Monitoring Service. So this new service is attached to the Land Monitoring Service, which is the one which includes Corinne Lancover. The implementation of this new service is under the responsibility of the European Environmental Agency, EEA. What have been the main activity in the last 2 years? The first important step was the product specification and the service implementation plan, which was made by the Aurora Consortium. Again, here you have the link to this document. Then there was the selection of the team devoted to the production, to the implementation of the service. The production consortium started its activity on the 1st January 2021. In the meantime, the environmental agency is assisted by an external advisory board, as I mentioned at the beginning, by European expert and by a supporting expert. Another milestone has been the definition of the validation approach and plan, which was done by the advisory board. Again, here the link to the document. And finally, we are now in the selection process of the validation team. There is a call for tenders, which is open in this moment, and which closes the 14th of June in 2 weeks' time. Here you have the link. About the production team is done by the original consortium. This is the name of the consortium, which includes 4 main actors: EGMS, which is the coordinator of this consortium, TRE Altamira, NORCH, and GAF. And then there are some subcontractors, which are Nazca from Italy, Earth Metrics, the Geological Survey of Norway, Hippo Labs, the Satellite Geodetic Observatory of Hungary, and the DLR. This is an important consortium. What are the key characteristics of this service? Well, the service aims to provide consistent, updated, standardized, harmonized across national border and reliable information regarding both natural and anthropogenic ground motion phenomena. The service will be based on Sentinel-1A and 1B data, that this data will be processed at full resolution. The service will make use of both ascending and descending acquisitions, and from the selection, measurement point selection, in the service, both persistent scatterers and distributed scatterer will be used. The service will, of course, generate the deformation map and deformation time series. For the regions that are affected by seasonal snow cover, the processing will be restricted to the snow-free scenes. For more details about the service, you can refer to this link in Land Copernicus EU, and also to the paper Crosetto et al. Published in Remote Sensing in 2020. More characteristics. The service will produce first a baseline product which covers from February 2015 to 2020. This baseline product will be followed by product updates every 12 months. In order to produce these, a total of 750 single loop complex scene that cover Europe will be used. For each stack, there is an average of 260 scene available. The total input to be processed for the baseline product equals 1.5 petabytes of uncompressed single loop complex images, and every year the volume will be increased by approximately 350 terabytes. Again, about technical details, you can refer to the poster session 1C of this event, which is presented by Costantini et al., European Ground Motion Service from INSAR processing to product dissemination. This is the coverage of the service. The service will cover all the Copernicus participating states. So basically, there is some lack of data in Switzerland and in the Balkans. Otherwise, we have a very nice coverage of Europe. I will describe briefly the three main products of this service. The first product is the so-called basic product, or level 2A. Level 2A includes deformation maps and deformation time series measured along the line of sight. This is a basic product because it is the closest to the raw data, because it is delivered for individual and consistent frame of the original SAR image stacks. And for each frame, the measurements are referred to a given reference point. This is a basic product. The calibrated product, or level 2B, in this product, the product coming from level 2A are mosaiced. So this product consists of an integration, a fusion of the information coming from interferometry and coming from a GNSS network covering Europe. The deformation, again, will refer to the radar line of sight. In order to generate the calibrated product, one of the challenges is to overcome the uneven availability of data across Europe. The product will be based on the UREF network, the PND, and the NGL station. Again, the level 2B will be generated at full Sentinel-1 resolution. Finally, we have the third product, which is the ORTHO product, or level 3. This represents a more advanced product, especially with respect to the basic one. It includes two main components, two main deformation components, the horizontal east-west and the up-down vertical component. This ortho product is obtained combining at the coarse resolution. We are not a full resolution. We are a resolution of 100 by 100 meters, and we fuse them, the ascending and descending INSAR results. So this is a summary of the processing. We start with a stack of Sentinel images. Through a INSAR processing, we generate the basic product. Through mosaicing and GNSS calibration, we generate the calibrated product. And through resampling and component calculation, we generate the ortho product or level 3. The product generation will be based on well-proven techniques. However, of course, the generation of such a big data set involves complex data processing, and the product generation will include a detailed quality control. Just to have an idea, the example of quality control will include the temporal coherence, will include the check of the density of the measurement points for different land cover classes. For instance, in continuous urban area, we expect to have more than 5,000 measurement points per square kilometer. We will do the consistency between different data coming from different orbits over the same area. There will be a comparison with GNSS, the data coming from GNSS station. There will be the analysis of the interferogram before and after the atmospheric correction. There will be comparison with the data coming from artificial reflectors. And very important, there will be a multi-provider harmonization, because we have this product, this data set will be generated by different providers. So it is very important to minimize the difference of these providers. And this will be done and checked, especially in the overlapping area between different providers. Product delivery plan. In the first quarter of 2022, so in less than 1 year, there will be the initial 5-year baseline delivery. And the baseline will span 2015 to 2020. Then in quarter 3 of the same year, there will be the first annual update, updating the data from 2021. And then the same quarter 3 in 2023, the second update, and Q3 2024, the third update, adding the data from 2023. So an ambitious delivery schedule. It's worth mentioning the dissemination of this project, which is a very important component. The EGMS product and services will be made freely available to everybody. A new data set, a new European geospatial data set will be generated, which is expected to generate new products and new service starting from this main data set. Beside the data, tools for visualization, exploration, analysis, and download will be available through a dedicated dissemination platform. Several user uptake activities are planned, which include workshop, trainings, webinars, etc. And also manuals, use cases, and good practices will be distributed through the service portal. All of this is because, of course, this service is ambitious and wants to be used by many different sectors, many different type of user beyond the community that is already using this type of data now. So we want to enter in new application fields, and in order to enter in new application field, it's very important to have a high acceptability of the service by the different experts. So in order to increase the acceptability, a validation activity is planned. A comprehensive validation process will evaluate the applicability and detection capability of the insert product through an independent assessment. And as I said before, the validation is subject of a separate call for tenders, which closes in 2 weeks from now. And this is everything for today. Thank you very much.
Thank you, Michele. Very interesting. Again, if anybody has questions, please enter them in the chat on the right-hand side. We're going to switch now from production of data to more application talks about usage of. And we're going to start, the next talk will be by Maria Bredal from the Geological Survey of Norway, and she's going to talk about using a nationwide ground motion service for landslide mapping. Go ahead, Maria. Perhaps you're still muted.
Now everything should be ready. So thanks, John. In this presentation, I want to give you all an overview on how we use the operational Norwegian ground motion service, how we use it to map, and how we use it to monitor unstable rock slopes throughout Norway. Norway, as a mountainous country with deep and narrow fjords and valleys, is especially susceptible for large rock avalanches. In historic times, such events have happened every century. This is an example from one such slope that fell into the fjord, causing a tsunami that took out several buildings and caused about 40 fatalities in the mid-1930s. So because of that, NGU is now currently working on systematically mapping and classifying all unstable slopes in Norway regarding their risk and their hazard. In the hazard assessment, it lies a number of geological and structural factors that is analyzed. For example, that could be how well developed is the backscarp and other limits of the unstable slope. Does the structures, the foliation, and the fractures, do they allow sliding along them? Because the more developed the unstable slope is, and then if the kinematics favors a collapse, the higher the hazard level. Another important factor that we assess is the displacement rate. The higher the velocity, the higher the hazard score. So based on INSA Norway and the nationwide data set, we can quickly do a first assessment of the velocity and then know at which unstable slope to focus our effort in order to classify them on a more detailed level. So it all started with systematic processing of ERS data in the mountain areas in Norway. This was very successful and led to us deciding to systematically also acquire and process RADARSAT-2 data from 2009 and onwards. But these data from the commercial satellite was expensive, and we only had data then covering the most landslide-prone areas in Norway, that being western parts of Norway and also northern Norway, and also some of the biggest cities, such as Oslo. So fast forward to today, what do we have? Today we have an operational map service that is open and freely available for everyone to use. The map service was launched in late 2018, and for now we have had yearly updates of the data, but this will change in the future with more frequent updates. This data is based on the Copernicus Sentinel-1 satellite that acquires a radar scene every 6 days. But in reality, lucky as we are in Norway, we are located so far north and the radar tracks overlap. So in anonymous part, in reality, we get images every other day. And a little side note here, we are also now currently exploring government-to-government cooperation between Norway and Sweden to evaluate the establishment of a joint service. This we hope will lead to processing synergy and of course benefits of a free and open service to the society, to both of us to both countries. So back to Norway. What have we found so far after the launch of the ground motion service? Firstly, and not surprisingly, the new data set, as exemplified in the graph here, led to the discovery of many new potential unstable slopes. Just within the first few weeks of quickly scanning through the country looking for slopes, we found more than 100 new ones. And secondly, and not surprisingly that either, most of these newly detected slopes are located. We found them in areas where we, from before, did not have any INSAR data coverage, and also in areas where we hadn't mapped before. So this is then areas in the gray dots here represent the newly detected slopes. So that is eastern parts of Norway, but the majority you see is found here in the high north. One such example is this side in this area here in the high north. It is about 900 meters wide, 300 meters high, and it displaces by a few centimeters per year. And if to fail, it could lead to a tsunami that again maybe could cause damage to the settlements just across the fjord. So yes, the nationwide dataset has helped us to identify new unstable slopes, but we also use it for monitoring. So at all unstable slopes that we have classified as high-risk objects, we have installed a network of corner reflectors. And compared to the map service, this data is processed more often. So twice a week, new data is uploaded directly into this monitoring system. One advantage of these corner reflectors are that we can follow displacements year-round, also in wintertime. And with year-round measurements, seasonal variations, or maybe an acceleration phase of the displacement can be more easily followed. This graph here, it relates to one of the unstable slopes that is classified as a high-risk object in Troms. This unstable slope shows a steady displacement for many years. But as you all know, INSAR displacement measurements can be a challenge to interpret because of their one-dimensional nature. And often we see a highly different displacement pattern in descending and ascending data sets. And therefore, it is not always easy to understand what this displacement that we see, what it relates to. Could it be an unstable slope that moves along a deep-seated sliding plane, or is the movement more superficial and rather, could it relate to permafrost processes, maybe such as solar fluctuations? So these are questions that we are faced with at almost every site that we map. And as you can imagine, this, of course, has an important implication for the outcome of the hazard assessment. One way to help answer this question is to exploit the different geometries of the different INSAR datasets. So by combining overlapping datasets, ascending and descending datasets, we can go from a one-dimensional movement vector along line of sight to a two-dimensional information in the east-west and the vertical plane. And this, of course, it relies upon a number of assumptions, also a number of site-specific assumptions. And I also would like to mention that our tool, that is the ArcGIS tool developed by NORS, Norwegian Research Center, it also allows us to choose various constraints for the movement, such as 0 north-south movement. We can choose maybe all movement downslope or movement along a certain compass bearing. And then, of course, the results will highly depend on that we have chosen the most likely constraint in order to have good results. So here, let's go back one. So here we have estimated 2D combined surface displacement for one such specific site in the more southern part of Norway. We calculated this using one ascending and one descending data set. And based on our geological understanding of the slope, after a few field campaigns for this site, we constrain the movement to only downslope. What we see is that in the vertical plane, as you can see over here, most of the movement is at the same rate throughout the slope. Maybe a little bit less here towards the upper end of the back scarp. In the east-west plane over here, we more easily can distinguish one area from another, this moving more towards the west. But for some sites, such as this one, we are lucky to even have a third INSA dataset from ground-based INSA. And this allows for an even more intuitive visualization of the kinematics of the unstable slope. So if we think back at the few figures I showed just now for 2D data at the same site, we see that it matches fairly okay. And from that, we can draw the conclusion that for this site, downslope displacement seemed to have been an okay constraint to have chosen. But plotting the velocity vector and dip across the profile along the slope, it allows for even a bit more intuitive understanding of the slope. So from the profiles, we can more clearly differentiate between areas of the slope displacing at a steep angle, such as up here, close to the back scarp, and some down here. See that it moves along a steep angle. Whereas other areas downslope here moves more slope parallel. So from this, we can maybe draw the conclusion that the steeper angled movement relate to sliding along a deeper plane. Various areas moving more slope parallel, maybe they relate to superficial creep of, in this case, rockfall deposits. So, but even though INSA and these higher order products are of great value to us, we also, and they make us gain a lot of information about sites from afar, we also see that we have to treat the data cautiously and that we have to interpret them in combination with field mapping data. So to summarize this, INSA and the Norwegian Ground Motion Service is a valuable tool for us to detect and also to map unstable slope, especially when we are looking at this at a national scale. The nationwide data set, it helps us to prioritize our resources based upon displacement rate of specific sites. And when going into detail on sites, we can use the displacement pattern to distinguish between different scenarios, which is, of course, an important input to the volume estimations and then also for the hazard assessment. And we see that visualization of multi-geometry inside provides us with a more intuitive understanding of the kinematics of different slopes, and it can help us to differentiate between different slope processes occurring at the same site. Thank you.
Thank you, Maria. That was really interesting. We're still running a couple of minutes late, so I propose leaving the questions until the question and answer session at the end. So I'd like to introduce our next speaker with slight change in the programme. This will be Mahdi Mortag talking about aquifer depletion in Iran.
Thank you very much. But I cannot share my screen, so I need permission. Yeah, wonderful. Yeah. Do you see my screen now?
We do, yes.
Okay. Thank you very much. Good morning, good afternoon, good evening, everybody. So my name is Mahdi Mortag from GFZ German Research Center for Geosciences and Leibniz University, Hanover. I'm presenting this work together with Mahmoud Haqiqi, who is a postdoc in our institute. So the title is Aquifer Depletion in Iran, a nationwide survey from spaceborne radar and in situ measurements. So, as you know, these groundwater wells provides important source of water to billions of people worldwide. So they provide 50% of global irrigation. So the 50% of global irrigation depends on this valuable source. And the studies have shown that overexploitation of these valuable sources has resulted into decreasing of terrestrial water storage in a number of places, for example, including Middle East and Arabian Peninsula, in other places like North China, India, and also Central Valley US. So a number of places in the world, they are suffering from this from decrease in terrestrial water storage because of overexploitation. So a recent study we just published also in Science shows that this is a sort of real, we have the risk at the global scale. So at the global scale, scientists try to study 39 millions of wells in 40 countries and estimated that around 20% of 20% of the wells are at the risk of running dry. And as a result, the people are trying to drill, these wells at a greater depth. But this doesn't help because all these wells, are located in areas where we don't have, more groundwater necessarily. So it's a really, global hazard at the moment. So we focus here in Iran. So in Iran also, we had this problem of overexploitation of water resources. So Iran is located in arid and semi-arid region. So we have several main catchments in the country. The largest one in the central catchments here, which actually sustain only 29% of the water resources. There are other catchments like, for example, this Persian Gulf, this one. And this Persian Gulf has most of the water resources, 50% of the water resources. So, I mean, the water resources are not evenly distributed, in this big country. And the problem in overexploitation of water resources started around, as you see here from 1980s, at the late of 1980s, because of the change in the policy, to make the country, being independent in the food and agriculture. So they started, allowing people to exploit water as much as possible, to be independent in the food and agriculture. But this has come at certain cost, and now, I mean, we have a huge problem. There is a huge problem in the water issue. So, some fancy solutions are now, it's a hot topic now in Iran. For example, some people suggest that we need to connect, create a new river from north to south, connecting Persian Gulf to Caspian Sea. So other people say that no, it's just enough, to connect, halfway to from north to the south. And then there is now there are debates, about building desalination plants along along the Persian Gulf. All these topics are hot debated now in the country. So our objective is that, okay, what is the implication of a stress on groundwater resources for the subsidence hazard in Iran, and can we evaluate the health and stability of this important hidden resource, which using modern remote sensing technology. So we focus on Sentinel-1. So Iran is well covered by Sentinel-1. So every 12 days, in both ascending and descending. So here in this study, we focus on descending analysis. So 10 descending orbits, 66 frames. So we have analyzed all the data from 2014, 2006 to 20, and so up to 8,000 Sentinel-1 images. Our processing strategy is that so we stitch all these SLCs, to make a large SLCs, and then we resample them to a reference image. And so we create a sparse network as similar to the method that presented this morning by our colleague in Italy. And so we consider the temporal baseline of 150 plus 50 days to be able to combine all interferograms together. And then we run the sparse network using Python and do tropospheric correction using Geckos. So when we do this, so we get this feature, this pattern. So as you see, so it's the first product that we derive. So even still after this Geckos correction, we see some patchy pattern of deformation. So shows that this Geckos correction is not sufficient to produce a clean product for us. Nevertheless, when we compare, for example, to a work that I did more than a decade ago regarding subsidence in Iran using NVSAT sensor, we appreciate the product that's provided by Sentinel-1. Every 12 days we have good coherence. We can have all this nice coverage of the data, and we can, although it's patchy, we can still see some nice hot spots, which clearly from our previous experience, we know that these are the locations of areas subject to aquifer compaction. So, Mahmoud, as part of his PhD, developed a further post-processing scheme. So I don't go into the details of that. So he developed a sort of a method, by splitting interferogram, and then he made a sort of image segmentation to detect phase anomalies, estimated the atmosphere for each pass, and then projected back for each pixel so that we can have pixel by pixel corrections for this large interferometry analysis. And the result shows that, he did a quite good job. So this is the original interferogram without correction. This is the interferogram that we get after Geckos correction, and using patch-wise processing that we get a sort of much better quality interferograms. And when we do the sparse analysis with these filter interferograms, then we are from this patchy pattern, so we reach to this one. So now we are in a position to see better all these anomalies, that are caused by compaction. And so we can do a sort of now more in detail geophysical analysis from this product, about to investigate the cause of all each compaction unit that we see in this nice INSAR map. So, and the result of this analysis shows that, for example, in the central catchment of Iran, so we have, in total in the country, we have around 300 basins suffering from heavy subsidence at the rate, some of them at the rate of 20 to 30 centimeter per year, and 160 of them are located in the central catchments. In the central catchment, I mentioned that it only encompasses 29% of the water resources. In terms of the number of subsidence, so it follows the central catchment by Persian Gulf here. So with 80 subsidence basins, but in terms of the areas, subsidence areas, the central catchment is followed by Caspian Sea here. It's a forest, so also a lot of agriculture going on for rice and other crops. So in terms of the area, so this Caspian Sea, so follows the central Iran. So then this catchment, for example, here, is the lowest one in both in terms of number of subsidence and also subsidence area. But this is eastern Iran, so it's the border of Afghanistan. Because of the security issues, there are not much also development here compared to other basins. So it's a very nice product that we can have, thanks to Sentinel-1, for the first time evaluate, okay, what's going on in each catchment in terms of subsidence hazard. Another issue that, okay, so we can then, thanks to this time series analysis, we can do a sort of first approximation of the long-term compaction versus seasonality, and then we can evaluate the amount of elastic to inelastic compaction throughout the country. And we see that, unfortunately, in a lot of basins, for example, in central Iran, in Persian Gulf, the inelastic compaction is more, because the ratio of elastic to inelastic is severely less than 1. In some of the basins, for example, this Urumia, which is here, and also Caspian Sea, I mean, the elastic deformation is higher. So at least, you know, the aquifers, you know, they are showing some response to the changes in groundwater variations. In other basins like Hürmand or Sarasso, also again the inelastic. Also, I mean, a few compaction, you know, aquifers are located. I mean, the deformation is mainly inelastic, so it means that it's dominated by long-term compaction. A nice study has been done recently by colleagues from US that shows that quantifies the amount of groundwater reduction from 2002 to 2015 based on in situ measurements for each individual catchment, which they have published in this paper. And then when we compare our INSAR result with their, you know, with these estimations, then we can estimate, you know, for the first time the storage coefficient, which is a very important parameter for groundwater management, and we can use to predict the future behavior of compactions in the country. So this is the value that we get for skeletal storage coefficients for each basin, considering the INSAR measurement. We constrain the compaction from INSAR, and then the changes in groundwater from the in situ measurements using these studies, and then so we can have this estimation for storage coefficients for the whole country. Another aspect is that, okay, what is the subsidence? This is in terms of the health of aquifer system. So another important aspect, okay, what is the effect of subsidence hazard to individual infrastructure? So we develop a workflow. So we extracted, you know, vector data from OpenStreetMap. So we try to develop everything using open source data and open source software. So we extracted railway, metro lines, roads, and then define a buffer zone. So we had our subsidence map from Sentinel-1. Then we use the Copernicus land cover, you know, it raster data 100 by 100 meter. And then we started to analyze, you know, how individual infrastructures have been affected by subsidence. This is the first product, for example, shows that, okay, in terms of land cover, so 11% of the total croplands in the country, very likely irrigated, have been affected by compaction. So in terms of build-up area, we see that 11% of the total built-up area in the country have been affected by subsidence, as have been shown here. So on the right, you know, when we incorporate this information from INSAR into our classification. In terms of, for example, railway and metro lines, we see that, for example, 8% of the railways in the country have been affected by subsidence. This is, for example, a close-up view for the railways in Tehran, so which is subsiding at a rate of 20 centimeters per year. And then we see that, you know, 17 metro stations and 15 kilometers of metro lines have been affected by heavy subsidence in this region. Another layer, you know, it's airports. So unfortunately, the majority of main airports have been affected by subsidence. This is international airport in Tehran. So we see that, I mean, it's subsiding at a rate of 5 centimeters per year. This is another airport in Isfahan. It's a famous city in Iran, touristic city. So it's also affecting by subsidence. And also, for example, Kerman here. So it's a very hub for agriculture, pistachio plantation. So we also see, you know, the whole airport is subsiding at a rate, the whole airport is subsiding at a rate of 10 centimeters per year. In terms of, for example, power lines and roads, so approximately 6% of the total roads and also 3% of the power lines, you know, high voltage power line transmission lines have been affected by subsidence. This is the first result that we have obtained through this GIS analysis by incorporating INSAR results and to figure out, I mean, individual infrastructures that are suffering from this subsidence and need, you know, regular maintenance, you know, because of this subsidence value. So in conclusion, so we have developed a workflow to reliably exploit large stack of Sentinel-1 data for subsidence displacement monitoring. So we have 13, we have detected around 300 subsidence areas. The central catchment in Iran is the most affected catchment by land subsidence. Unfortunately, the major component is long-term subsidence inelastic deformation that we see in our results. And up to now, we haven't developed machine learning techniques, but now with all this data and layer of information that we have, so our next step would be to develop a sort of, we want to go for deep learning and data fusion approach for automatic assessment, clustering, modeling, and updating of subsidence hazard, in the national scale. Thank you very much. I hope I'm time.
Thanks. I guess we'll now have about 10 minutes left, 9 minutes left for question and answers. I guess we'll start with what should be the first speaker about the corner reflectors. How do you evaluate phase stability for the Slovenian case with respect to nearby natural scatterers? Are there nearby corner reflectors? Also, temperature phase correlation should not be an issue if it's time stationary. It can be modeled, but how about the long-term phase drift?
Okay, can you hear me? Can you hear me?
Yes, it's fine.
Okay, fine. Sorry. Well, in general, because we are testing the stability of the devices, we look for very stable area. In the case of the measurements, there is also the opportunity to check the stability because the active reflector was installed together with the GPS system. By the way, especially in long, it's correct that one of the challenging issue of the active reflector is the long time shift of the phase, and for this reason we are trying to collect a very long temporal series, especially in the where we have the stable installation, to evaluate along at least two years and more the stability of the device. Of course, when you install the active reflector, when you have achieved the stability we are looking for, any correction can be made according to simple model deformation or other things. I hope this can be reply enough. We're checking the chat for the.
Thank you, Guido. So I suggest we do one question per presenter first and then see how many more we have time for. So I would say questions for Riccardo Lanari. I know, Riccardo, you've already written some answers to some of the questions, which I think will be pasted into the Slido chats for any that we don't have time to address in person. And then I would say, so picking one of the questions that you've been asked, how would you handle the reference points for the whole EU when doing a mosaic?
Yeah, Raka, essentially we have one reference point for each frame. So essentially you see we process in tails 175, if I remember correctly. So each of these has one reference point. And essentially we pick it up by looking at the GNSS information we use.
Sorry, I was looking for my unmute again. That was a good answer, thank you. Michela, about the EGMS, one of the questions is how will the long wavelength tectonic movements be handled? And I'm not sure what they mean by handled. Perhaps how will they be presented or displayed or derived?
Well, there will be the fusion with the interferometric results and with the data coming from the GNSS station. So the long wavelength, the long wavelength will be basically captured by the GNSS stations.
Thanks.
Okay.
Maria, okay, go ahead.
No, after you, John, sorry.
Okay, sorry. The next question is from Maria Bradell. It has to do with the size of unstable rock slopes. What is the minimum size of an unstable rock slope that can be detected?
Okay, so first of all, maybe I should mention that in the mapping program that we do looking for unstable slope, we are looking for quite large volumes, bigger than 100,000 cubic. So we are not, at least systematically, looking for anything smaller than that. But smaller size than that, I think, will largely depend on, for example, vegetation and also other geometrical effects such as shadow angle of the radar and layover effects. We can see smaller things, but again, we are not systematically looking at it, and also it will depend on the resolution in our of the Sentinel-1 image, which is 5x20, of course.
Thank you, Marie. Okay, and a question for Mahdi. So the comment was great work from the person asking the question. How do you detect the subsidence zones? Is that done manually or through a computer-assisted approach? And have you investigated the relationship between seasonal changes in groundwater table and the land subsidence and uplift?
No, it's not manually. It's as I discussed, it was a part of the processing algorithm to detect phase anomaly, extract them, and so on. So it was implemented within the processing approach, but not fully automatic. Like this machine learning approach or deep learning approach. So, but it was implemented in our programming, and in our scripts, to detect phase anomalies and extract them. And regarding this seasonality and uplift, yes, we have investigated. I mean, the part of the presentations in which we discussed about, the relation between long-term compaction and also the seasonality in the time series. This is the part which for us represents information about, the health and sustainability aquifer in the country. So yes, we have investigated because we have a long time series, so we can investigate this information.
Thank you, Mahdi.
I guess, do we have time for one or two more questions? We should remind everybody that there are further sessions later on today and tomorrow, and also the poster sessions, please join them. One more question for Ricardo. When you use short-term temporal interferograms, sensitivity to movement is lower than when you're using long temporal baselines. And what do you think about this limitation, and how do you solve it?
John, as I answered on the chat, so I don't know if it is visible, essentially we do not have any model, so this is not a big issue, because if you have coherence and you do not have significant wrapping errors, you get immediately the accuracy, because you do not have to minimize any linear or nonlinear model. The time series gives you the accuracy that you need.
Okay, thank you. And then another question for Michele. Do you plan to deliver other high-level products, such as time series classifications, clustering, for example, in the future, to produce a more friendly product for non-experts in interferometry?
In this moment, the products that are planned are those that I explained in the presentation. This is evolving as a project, and I cannot exclude that there will be more high-level products in the future. Also can be that some groups, research groups, etc., use this data and want to share the tools for making a more advanced analysis of the data. This will be a possibility. Okay, but for the moment is not planned.
Okay, I'm just looking down the list for which speakers still have questions they haven't answered. It looks like there are still some for Riccardo Lanari that we haven't discussed verbally. I know you wrote answers to some of them, which may have been posted in the chat by now. Are there any that you, in the list of questions, Riccardo, that you think are particularly useful to discuss?
Okay, let me see. Perhaps the story of the overlap, because somebody asked, how about the overlap of the different frames? On my point of view, the overlap of frames, it's interesting. It should be not cancelled out, because there, because of different line of sight, you may have intriguing information to assess. So in the overlap region, instead of removing these areas, I think it's important to maintain in order to try to catch this additional information due to different line of sights.
Okay, thank you very much. I guess everybody now has a half an hour break. Please take a good rest and come back refreshed for the next session, which starts at 11:30, continuation of this session. Thank you, everybody.
Thank you.
Thank you to all.
Thank you.
Thank you for participating. See you in a bit.